Hey everyone, welcome to today's Explainer. We're unpacking a fascinating, high-stakes detective story straight out of Uber's engineering labs. It's not exactly a true crime mystery. Well, maybe it's a crime against compute efficiency. We're talking about hardware, data, and the hidden limits of deep learning infrastructure. When you're training the massive AI models that power a global marketplace like Uber, efficiency is quite literally everything. But what happens when the very infrastructure that's supposed to make you faster becomes the exact thing slowing you down? Today, we're going to explore how Uber tracked down a massive system bottleneck and totally re-engineered how they feed data to their machines.
To really get a grasp on this, we got to set the scene. Imagine you're working with a data set that is just staggeringly huge. We are talking tens of terabytes of data, tens of billions of rows, hundreds of unique features. And to process all of this, you've provisioned an army of highly advanced, extremely expensive GPUs. Think of these processors as the absolute supercars of the computing world, right? They're built to consume data at blistering speeds. But here's the massive problem. They're just waiting around. It's like having a grid full of Formula One cars parked on the track, just sitting there waiting for fuel.
Okay, let's dive into this staggering metric. The Uber team took a hard look at their system, and what they found was frankly shocking. Their high-performance GPUs were only being utilized about 10 to 15% of the time during training. Just think about that. That means for roughly 85% of the time, these incredibly expensive, powerful machines were doing absolutely nothing. Zero. Just idling. In the world of large-scale machine learning, that kind of inefficiency, it's a massive drain on your time and your compute budget. It's totally unacceptable.
And this brings us right to the core of the issue, what we'll call the starving GPU mystery. The engineers dug in and discovered that the system was rereading the exact same Parquet data files from their Hadoop Distributed File System, or HDFS, over and over again for every single training epoch. This constant fetching across the network caused a massive I/O and CPU bottleneck. So the GPUs weren't lacking compute power at all. They were literally starving for data. The pipeline just couldn't serve up the numbers fast enough to keep them fed.
So, how exactly do you hunt down a hidden bottleneck like this? Let's get into the investigation.
Knowing your GPUs are starving is one thing, right? But actually fixing it requires some seriously methodical detective work. The engineering team didn't just throw things at the wall to see what stuck. They used this brilliant process of elimination. First up, they benchmarked larger models. By artificially jacking up the model's complexity, GPU utilization jumped to 80%. Okay, so that proved the model size wasn't the issue. The GPUs definitely had capacity. Second, they forced a small subset of data right into a RAM cache. Instantly, utilization spiked past 60%, which confirmed the network I/O from HDFS was definitely a primary villain here. But here's the twist. When they finally implemented a local disk cache to avoid that HDFS network latency entirely, they expected a huge win. And nothing happened. Utilization stayed super low. It turns out solving the network latency actually uncovered a hidden secondary problem.
That hidden culprit? The compute wall. See, getting the data onto the local disk was only half the battle. The data was stored in a format called PyArrow, but the GPUs, they needed it in NumPy. And converting from PyArrow to NumPy is incredibly CPU intensive. The system was trying to do this transformation just in time, right on the main thread, for every single batch of data. So, incredibly frustratingly, even with the data sitting right there on the local disk, the CPU just couldn't convert it into a ready-to-train format fast enough. The main thread was completely bogged down doing data conversion, totally blocking the GPU from getting its next batch. You fix one massive bottleneck only to smack face first right into another one.
Okay, so now we know what we're up against. Let's talk about optimizing that data transformation.
Once the team exposed the true nature of this double bottleneck, the network latency combined with that nasty CPU contention, they were able to architect a real solution. They built what we can call a two-pillar architecture. First, they implemented push-down transformations. So instead of the main thread handling all that heavy PyArrow to NumPy conversion, they pushed the heavy lifting down to the Petastorm worker pool. This parallelized the workload across multiple threads and completely freed up the main thread to do just one thing: feed the GPUs. Pillar number 2, local disk caching. They used this to store the pre-transformed NumPy arrays. By caching the data after the conversion happened, they completely bypassed that CPU wall on any subsequent reads.
But as you might guess, in engineering at this massive scale, solving one problem almost always introduces a new one. So here's the technical dilemma they face next. How exactly do you cache a dataset that is physically larger than your local hard drive without completely ruining the AI's ability to learn? See, deep learning requires data to be fed in very specific, randomized ways. If you use standard caching rules like LRU eviction, where you just kick out the oldest data, it would completely break the training cycle. The AI needs to see every piece of data exactly once per epoch. Evict data too early, and boom, you're back to fetching it over the slow network again.
And this brilliantly illustrates the kind of real-world development hurdles they had to overcome. Since the datasets were bigger than the disk, they totally abandoned standard eviction and built a strict quota management system instead. They basically filled the disk and only fell back to the network as an absolute last resort. Then, to preserve that critical randomness for the AI, they decided to cache smaller row groups instead of pre-made batches, and they added a final, lightning-fast memory shuffle right before hitting the GPU. Oh, and pushing the hardware this hard created what they called zombie threads. These are I/O tasks stuck on slow network calls that just refuse to die, freezing the entire array cluster. To fix that, they had to implement robust sentinel logic and super strict timeouts to safely kill off those blocked threads without tanking the whole training job.
All right, problem solved, right? Well, not quite. Enter the ghost in the machine, the reproducibility problem.
Just as they finally cracked the throughput issue, this completely new, deeply frustrating problem emerged from the shadows as they scaled up. Engineers were running two identical training jobs. I mean, exact same code, exact same data, same fixed random seeds, the whole shebang. Yet run 1 and run 2 were speeding out varying results. There was an unexplained run-to-run shift in their mean average precision, or MAP, of about 0.5%. Now, 0.5% might not sound like much. Actually, scratch that. In the precise world of deep learning, a 0.5% variance is massive. It made it practically impossible to evaluate if a new model architecture was actually an improvement or if that run just got lucky.
So the huge question became, where in the world was this randomness hiding? Petastorm, which is the data loading library they were using, already handled its high-level operations deterministically. Shuffling row groups, partitioning data, all tightly controlled by the seed. The high-level logic was totally sound, which meant the variance had to be seeping in from somewhere much, much deeper within the system architecture.
It was time to pull back the curtain and unmask the race conditions.
To find the real culprit, the team had to look closely at how the multiple worker threads were actually talking to each other. In the old architecture, all those parallel workers shared a single ventilator queue to get their tasks, and a single results queue to hand back the data. But because thread scheduling and execution speeds vary constantly at the microsecond level, the workers were essentially racing each other. Whoever finished first pushed their data first, which inadvertently shuffled the order of the data being fed to the GPU. Bingo. To fix this, they gave every single worker its own dedicated queue. They set up a deterministic, round-robin assignment for handing out the work, and they upgraded their legacy random number generators to a modern, reliable standard, specifically NumPy's default RNG. By separating those queues, they completely eliminated the race conditions, and they did it without sacrificing a single drop of parallel processing speed.
Okay, so let's look at the massive payoff from all of this. After all that intense detective work, the system profiling, the complete architectural redesign, it's finally time to look back at that terrible starting metric. Remember, they began with a really dismal 12% average GPU utilization. But after deploying the pushdown transformations, the local disk caching, and those dedicated worker queues, GPU utilization absolutely skyrocketed to over 60%. That is a 5 to 6 times increase in utilizing their most expensive hardware resources, just an incredible win.
And the real-world impact of that jump is spectacular. End-to-end training time for these massive models plummeted from 22 hours down to just 3 hours. That represents a whopping 80% savings in compute costs. But honestly, more importantly, it completely changes the engineering workflow. An engineer can now test a model, tweak it, and test it again in a single afternoon rather than waiting a full 24 hours for one iteration. Plus, that maddening map shift we talked about, it dropped down to roughly 0.13%, which completely restored their absolute trust in their evaluation data.
So, what does this all mean for us? If you take away only one thing from this explainer, let it be this thought. Sometimes the biggest gains in AI don't come from a new model architecture, but from optimizing how you feed data to the one you already have. At massive scale, efficiency isn't just about writing cleaner code. It is about deeply understanding the physical interaction between your software, your data, and your hardware. It really highlights the absolute necessity of full-stack orchestration. Because honestly, you can design the most brilliant neural network in the world, but if it's starving for data, you're just wasting your potential.
Which leaves us with a critical question to reflect on as we wrap up. Take a good look at your own infrastructure.
Are your most expensive computing resources secretly just waiting around on your slowest data pipelines? It might be time to do some detective work of your own. Thanks so much for joining me for this explainer, and keep optimizing.